Welcome back. This is Mr. Thompson again. This time we're looking at section 1-2. Still talking about the rate of change, this time looking at different examples by equation, graph, and tables. So let's go ahead and get started in this. We looked at equations with section 1-1, so it's not going to be as much about equations this time. Now more about the graph and table representations. So let's take a look at example number 1 from the book, where it says, and by the way, this is on, example 1 is on page 7. Example 1, figure 1-2a shows the graph of a function at x equals a, x equals b, and x equals c. State whether y is increasing, decreasing, or neither as x increases. Then state whether the rate of change is fast or slow. So let's go ahead and take a look at the picture. It is an XY graph. Probably looks a bit better than this, but oh well. With, let's make this a different color, a line that looks something like this. And then it gives us the points A, B, A, C, that one's C, and B. It wants to know what the rate of change looks like at f of A, f of B, and f of C. All we have to do that is take a look right where our dotted lines cross my green line. At A, this looks like a pretty steep line. It is steeply going up, so f at A is increasing quickly. F of B, well, over here, looks like it's starting to decrease, but not as quickly. So it's decreasing slowly. And f of C is an interesting one. It is neither increasing nor decreasing. This is right where the line is flat, right where it turns around, so it is neither. So yeah, for this, pretty much all you got to do is look at the graph and see if it's steep or not, and if it's going up or down or not at that moment. Now, let's take a look at another example. Let's look at example 4. 4 gives us a good example of a table. So this is on page 9. In this one, we have a mass hanging from a spring, bouncing up and down. So let's say this is my ceiling, and let me make my string, and here's my mass. So it is bouncing down, back up and down, up and down. Now, once again, it does not give us an equation. This time we are given a table of values. So we have T of S, and we have Y, which is our feet. So time in seconds, and our distance in feet that it is hanging. Time in seconds starts at 0.2 and counts up by 0.1. So 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0, and 1.1. Now, our distances we have is 3.99, 5.84, 7.37, 8.00, 7.48, 6.01, 4.16, 2.63, 2.00, and 2.52. Now, we want to know how fast is it moving at t equals 0.3, t equals 0.6, t equals 1.0. Now, this time, once again, we cannot use equations, so we can't come up with that. However, we can use our table of values. So firstly, let's look at time of 0.3. Right here, so we're going to look at the change from here to here and from here to here. So let's check out my calculator. So from 3.99 to 5.84, so I take 5.84 minus 3.99, 1.85, and then my next one, 7.37 minus 5.84, whoops, that should be a 0.84, 1.53. Now, both of these is a rate of at 0.1 seconds. And so when I divide by 0.1, I get 18.5 and 15.3. Notice all I'm doing is moving the decimal over. Now, what I want is the average of these two, so I'm going to add them up, divide by 2, and that will be my average rate of change, which winds up being 16.9 feet per second. Now I'm going to do the same thing at 0.6 and 1.0. So at 0.6, we're looking right here. So 7.48 minus 8, this time we're in the negatives, negative 0.52 at 0.1 seconds. 6.01 minus 7.48, I get negative 1.47, once again at 0.1 seconds. When I divide by 0.1, I'm moving my decimal, so I get 5.2 and 14.7. Look at the big difference here. 5.2, 14.7. That's a pretty big difference. Sorry, both these are negatives. When I take the average, we're going to have quite a bit of an error there, but that's what we want right now. So my average of negative 5.2 and negative 14.7 is negative 9.95 feet per second. Sorry, getting kind of squished in there. I want to make sure that's an arrow. It's not looking like an arrow. Let me redraw those so you don't think those are sevens. Arrow. Now, same thing at 1.0. So here at the bottom, so 2 minus 2.63 is negative 0.63. 2.52 minus 2 is 0.52. Both these over 0.1 turns into negative 6.3 and 5.2. These are pretty big different also because one's negative, one's positive. So I take my average and I wind up with negative 0.55 feet per second. So notice how the speed is changing, which would make sense because the spring falls down, stops, bounces up, stops, falls down, stops, and repeats until it stops. So that is graphs and tables. We combine that with equations from 1.1, and we have tables, graphs, and equations. Now, a couple loose ends to tie up that the book addresses. At the start of section 1.2, it gives a reminder of what different functions look like when graphed. So we have linear, quadratic, polynomial, power, exponential, rational algebraic, so I'm just going to put rational functions, absolute value, and last one, trigonometric. I'm just going to put trig, as in trig functions. Now, linear, hopefully you should know, is the form y equals mx plus b. You should know that from freshman year, heck, even from middle school. And our graph looks like a straight line, either up, down, whatever. But it's going to be a straight line. Now, quadratic has a bunch of different forms. However, the most standard form is y equals ax squared plus bx plus c. And this graph is a parabola. Whether up or down, skinny or wide, depends on a, b, and c. Polynomial is basically an expanded form of a quadratic with a higher exponent. So I'm just going to go y equals ax3 plus bx squared plus cx plus d. And since this is an exponent of a 3, it's going to look something like this. Remember, the exponent tells you how many directions you are going. Exponent of 2, down then up. Exponent of 3, up then down then up. 1, 2, 3, 1, 2. Power functions. Power functions have an x to a power, which is similar to what we had, but doesn't have everything else. So y equals, let's just say ax to the n. Let's use the one the book gives us. Ax to the n, so it's our variable to a power. And this, it's going to look something like this. Goes up. Let's see, let me double check. Ax to the n is going to be either a quadratic with ax squared and then b and c are 0, a cubic like this one, so it can be a parabola, it can be a cubic, it can be a bunch of different ones. Once again, it's going to have curves relating to the exponent. Exponential, this is the one I was confusing for a second, y equals ab to the x. This time our variable is in the exponent, and this one shoots up, usually. Now, if x is anything less than 1, it's going to have some different things going on. But standard form, this is it. Rational is basically a polynomial over a polynomial, so I'm going to write poly over poly. And these ones start looking pretty weird. Just give a kind of simple example. That would be a rational. Absolute value uses absolute value, which are these brackets which make everything positive. So if I have a graph, absolute value is going to be a V shape. And lastly, a trig function. Let me scroll down a little bit. Can be sine, cosine, tangent, any of those things. Let's just say y equals sine of x. And this would give us a sinusoidal wave pattern. Pretty similar to that. So make sure you can recognize these, how many are there? 8 types of functions and their general equation forms. Now, I'm going to go ahead and stop with the examples and pick out a problem from the problem set to go over in my next video that will be attached to this one.